In this video, we are going to talk about how we can use the derivative of a function to find out information about the graph. So we're going to start this using something that we mentioned before. And so if we look at the following graph of a function, where this is point A, point B, point C, and then point D, in this graph, notice that we are increasing from A to B, meaning that the function is going up in value. And if we were to draw all of our tangent lines to the graph, all of them are positive from A to B. So we're increasing on A to B, and the derivative is positive. Then on B to C, if we were to draw all of our tangent lines, notice that they are all negative. But we are also decreasing on B to C. We're going to smaller values. So we are decreasing on B to C, and the derivative is negative. And so this is not a coincidence. This is an idea that we have mentioned before, but we're going to now state it formally, and it just follows exactly what we just saw in this graph. And so if we let f of x be a differentiable function on the interval A to B, then the following is true. So first, if f prime of x is greater than 0 on the interval A to B, then f is increasing on the interval A to B. And second, if the derivative of f is less than 0 on the interval A to B, then f is decreasing on that interval A to B. And so this is an idea that we have mentioned before. We're just making it more formal. And so when the derivative is positive, we are increasing. When the derivative is negative, we are decreasing. And so we can make use of this to figure out when a function is increasing and decreasing. So we're going to look at an example of doing so. And so we want to find where the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. So we want to figure out when this polynomial is increasing and decreasing. Now drawing the graph of this would be fairly challenging, but we can use the derivative and the fact we just mentioned to figure this out. So we're just going to take the derivative and figure out when the derivative is positive and negative. And so taking the derivative of f, using the power rule, we're going to get 12x cubed minus 12x squared minus 24x. Just using the power rule on each piece. Then factoring 12x out of everything, this gives us 12x times x squared minus x minus 2, which this factors then as 12x times x minus 2 times x plus 1. And so that then is our factorization. So this is the derivative. Now we want to figure out when the derivative is positive or negative. And so the way we do this is we're going to figure out the critical points to start with, as the derivative can only change signs when we pass over the point 0. That comes from the intermediate value theorem, which just says in order to go from a negative to a positive or positive to negative, you have to hit 0. So we're going to figure out when the derivative is 0, and then just break it up into intervals based on where it's 0. And so the critical points are pretty easy to identify with how I factored it. And so our critical points are when x equals 0, 2, and minus 1. And so this then breaks up the number line into 4 intervals. We have the interval from negative infinity to negative 1, negative 1 to 0, 0 to 2, and 2 to infinity. And so these are the 4 places, the 4 intervals that we have to check, in a sense. And it's coming from the fact that on that entire interval we have to keep the same sign in the derivative, because we can only change signs when we cross over 0, which is at those points negative 1, 0, and 2. Now the way that we tend to do this is I'm going to organize it in a table, and then I'm just going to pick one point from each of these intervals and figure out what is the sign of the derivative at that point, and that tells us on that whole interval if it's positive or negative. And so let's set up our table. And so first we have our interval. And then, as I said, I'm going to pick a test point, which is just any point in that interval. And then I'm going to figure out what f prime of x is. And then we're going to talk about what f of x is doing based on that. So we first have the interval from negative infinity to negative 1. Then negative 1 to 0. 0 to 2, and then 2 to infinity. Remember, the derivative is 12x times x minus 2 times x plus 1. So I'm just going to pick any number in the interval, negative infinity to negative 1. I'll pick negative 2. For negative 1 to 0, we'll use negative 1/2. 0 to 2, we'll use 1, and 2 to infinity, we'll use 3. We're just picking some number inside of each interval. And now I'm going to plug each of these test points into the derivative. So plugging negative 2, when I get 12 times negative 2 times negative 4 times negative 2 plus 1, which is negative 1. And so taking this product, we get negative 96, and that's less than 0. And so since we're less than 0, that means that f is decreasing on that interval. So on the entire interval, negative infinity to negative 1, we must be decreasing because the derivative has to be negative on that whole interval. Now negative 1 to 0, we have 12 times negative 1/2 times negative 1/2 minus 2 is negative 5/2. And then negative 1/2 plus 1 is positive 1/2. And this product then is 18 over 4. 18 over 4 is positive, so we are increasing on the interval negative 1 to 0. Now plugging in 1, we have 12 times 1 times negative 1 times 2. So we get negative 24 out of this. And so we are decreasing on the interval 0 to 2. Now plugging in 3, we have 12 times 3 times 3 minus 2, which is 1, times 3 plus 1, which is 4. And this is 144, which means we are increasing as that is a positive number. And so we're able to figure out each of these intervals, what we're doing, based solely on just finding the interval from the critical points and plugging stuff in. And so to summarize what we have found then, we have found that we are decreasing on the interval negative infinity to negative 1, union 0 to 2, and we're increasing on the interval negative 1 to 0, union 2 to infinity. And all this really amounted to doing was taking the derivative, figuring out where it's 0, and then picking test points from the intervals where it's not 0 to figure out when we're increasing and decreasing. Now, one benefit of this is that if we know how we're increasing and decreasing, that actually tells us more about minimums and maximums. And so if we look at a graph for a second, notice that the point where I change from increasing to decreasing is a maximum. And a point where we change from decreasing to increasing is a minimum. And this is not a coincidence. If you were going up and then started going down, that point where you changed is going to be the largest possible value in the area, so it'll be a local max. And if you were going down and then started going up, then that point where you changed from going down to going up will be the smallest value nearby, and so it's going to be a minimum. And so this then gives us the following fact. And so this is called the first derivative test. And it's a way of checking if critical points are minimums or maximums. And so it says, suppose C is a critical number of a continuous function f. Then we have the following. So first, if f prime changes from positive to negative at C, then f has a local maximum at C. Second, if f prime changes from negative to positive at C, then f has a local minimum at C. Then third, if f prime does not change signs, at C, then f does not have a local min slash max at C. So in other words, if we didn't change signs, then that is a critical point that is not leading to a minimum or a maximum. Now, one thing to note here is I am saying critical point in this situation, or critical number. These include places where the derivative just does not exist. And if you have points where the derivative does not exist, those are also places where you could change from increasing to decreasing. You're not continuous, and so it's possible for the derivative to just flip signs from positive to negative if it's a place where the derivative just doesn't exist. So those are places to still check. So we still do check those points where the function's derivative doesn't exist, just like we did before. So when we list these critical points or critical numbers, you do list points that the function f is defined at, but f prime is not defined at. So the other kinds of critical points. And so what we're going to do now is we're going to use this function that we looked at a second ago and figure out where it has local minimums and maximums based on the first derivative test. And so this is just a continuation, so we want to find the location of the min slash max of f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Now, we've already done most of the work for this problem. This is the same function we had a second ago. And so we already know where we're decreasing is negative infinity to negative 1, union 0 to 2. And we're increasing on negative 1 to 0, union 2 to infinity. And so from here, we can figure out the x-coordinates of our local minimums and maximums. And to get the y-coordinate, you just plug it into f. And so we have our local min and our local max. And again, I'm just giving the x-coordinate here. To get the y-coordinate, you just plug it into f. And so for our local min, notice we were decreasing, for our local max, we were decreasing from negative infinity to negative 1, and then we started increasing at negative 1 to 0. So just using this first piece. So we went from negative infinity to negative 1, and then changed to increasing at negative 1. So we were going down, and then we started going up. So this is a local min. And now from negative 1 to 0, we were increasing, but then we started decreasing at 0. So 0 is going to be a local max. We were going up, and then started going down. Then we're going down from 0 to 2, and start going up at 2. So a local minimum at 2. And so these are local minimums and maximum locations. Negative 1 and 2 are local mins, and 0 is a local max. If you plug those in, the point is negative 1, comma, and then we'd have 3 times 1 plus 4. So 3 plus 4 is 7, minus 12, minus 5, plus 5. So we get negative 1, 0. And then at 2, we're going to have, I'll actually write this one down. So if we plug in 2, we have 3 times 2 squared is 16, minus 4 times 2 cubed is 8, minus 12 times 2 squared is 4, plus 5. So we have 48 minus 32 minus 48 plus 5. And so this gives us negative 27. So 2 comma negative 27 is our other local min. And then if we plug in 0, we're going to get out just the number 5. So 0 comma 5 is our local max. And so we found our local minimums and maximums just using this fact. So now let's look at another example of doing this process. And so next, we want to look at the function. We want to find the local min and max values of f of x equals 1/3 x cubed plus 7/2 x squared plus 10x minus 6. Okay, so we first are going to take the derivative of this function. So taking the derivative, we have 1/3 x cubed becomes 1/3 times 3x squared, so we're going to get just x squared, plus 7/2 times x squared's derivative is just 7x. Then the derivative of 10x is just 10, the derivative of 6 is 0. So we get x squared plus 7x plus 10 is our derivative, and this factors as x plus 5 times x plus 2. And so now that we've got the derivative and we factored it, we can find our critical numbers. And so our critical numbers are places where the derivative does not exist or is 0. The derivative is a polynomial, so it always exists. So the critical numbers are just where it's 0, which is when x equals minus 5 and minus 2. So minus 5 and minus 2 are critical numbers. That means we can then set up our table using this. So we have our possible intervals, our test point, f prime of x, which again is x plus 5 times x plus 2. And then we have what is f doing. And so our first interval is negative infinity to negative 5. And then negative 5 to negative 2. And then negative 2 to infinity. And now we pick test points, which again, it can be any point in the interval. Normally I pick integers that are fairly small or easy to plug in. So negative infinity to negative 5, our test point will be negative 6. Negative 5 to negative 2, we'll use negative 3. And negative 2 to infinity includes 0. If 0 is a possible test point, that's usually your best guess. 0 is very easy to plug into basically everything. So now plugging these in, we're going to have negative 6 plus 5 times negative 6 plus 2, which becomes negative 1 times negative 4, so we get positive 4. So we're increasing on this first piece Plugging in negative 3, we're going to have negative 3 plus 5, which is 2, times negative 3 plus 2, which is negative 1. And so we're going to get out negative 2, so we're decreasing on this interval. Then plugging in 0, we get 5 times 2, which is 10. So we are increasing on the interval from negative 2 to infinity. And so looking through this, we can find where we have our local minimums and maximums. We went from increasing to decreasing at negative 5. So we have a local max at negative 5. Because we went from increasing to decreasing, we have a local min at x equals negative 2 as we went from decreasing to increasing at negative 2. Now we did technically ask for the values, so if you plug in the points, if you plug in negative 5, you get negative 5, and then negative 10 to the 1/6. And plugging in negative 2, you get negative 2, and then negative 14 2/3 and 2/3. And again, you're just plugging them into the original function f here, which is why we have fractions, because we had fractions in our original f. And so that's how we can find critical values, whether they are minimums or maximums, using this idea of increasing and decreasing.